Hello, welcome to the video on solving compound inequalities. In the previous two videos, we looked at compound inequalities, graphing them on a number line, writing them in interval notation. And now we're going to solve. So we're going to solve symbolically using what we know about algebra, and we're going to be left with a compound inequality to graph and write in interval notation. And we're also going to talk about what it means to check your solution. So if I have a compound inequality, like this first example, I want to just use what we know about solving linear inequalities, and we just have two of them to solve. So in this first example, we'll add 3 to both sides. So we get -4 is less than or equal to 2a. Divide both sides by 2. And I get -2 is less than or equal to a. I did not have to flip that inequality symbol because I didn't divide, or I divided both sides by +2. Dividing by +2 will not change that inequality symbol. And what's important to note is that and kind of continues out throughout this problem. So over here on the right side, we're going to solve 3a plus 1 is less than 7. We want to subtract 1 from both sides, so I get 3a is less than 6. And dividing both sides by +3, I get a is less than 2. So we have this compound inequality solution. Now this looks like what we were graphing from last time. Reminder that here, if it's -2 less than or equal to a, we can change that to a greater than or equal to -2. And we have a is less than 2. So let's graph this, see what's going on. 0, +2, -2. And I'll switch to color coding here. So I'll do the first one in red. Where is a greater than or equal to -2? Well, greater than goes to the right. It can be equal to, so we're going to use the bracket. Let me shade this direction. A less than 2, I'll put that in green. Where is a less than 2? Well, we can't include 2, so we're going to use a parentheses, and less than goes to the left. So we have an and statement. So what does that mean? That means it has to be, whatever a is, has to be true for both of these. It has to be greater than -2, and it has to be less than 2. So is 0. So we're going to talk about checking solutions. This is part of that checking process. So I'm going to out to the side, kind of put, I'm going to check this, label my work and check it. I'm going to check, is 0 a solution? Okay, we aren't going to say the solution because the solution is everything that gets shaded. So is 0 a solution? Well, we want to check with our original inequalities. So -7 less than or equal to 2 times 0 minus 3. Is -7 less than, so that'd be 2 times 0 is 0, -3. Is -7 less than or equal to -3? Yes. So 0 is a solution to the first inequality, but it also has to be a solution to the second one. So we'll check 3 times 0 plus 1, is that less than 7? Well, 3 times 0 is 0, plus 1 is 1. 1 less than 7? Yes. So they're true for both. So yes, 0 is a solution. And so we're going to make sure that whatever we shade, it includes 0. Let's go out to the side here and check 3. Is 3 a solution? So let's check our first inequality. -7 less than or equal to 2 times 3 minus 3. So is -7 less than or equal to, well, that would be 6 minus 3 is 3. Is -7 less than 3? Yep. And we want to check the second one because it's and. It has to be true for both. 3 times 3 plus 1, is that less than 7? 9 plus 1 is 10. Is 10 less than 7? Nope. And this has to be and. So this implies 3 is not a solution. So it should not be shaded out there. Well, that makes sense because it's only red. It's not both red and green. So when we're looking at red and green, what's red and green? This region between -2 and 2. So our solution is -2 up to, but not including +2. So in interval notation, the solutions to this compound inequality are -2 to +2. That implies an infinite amount of numbers. It doesn't mean that there's only 2 solutions. That means everything that can be possibly graphed on this number line, -1/2, -0.11111, 1.9999, those are all solutions to this compound inequality. Every number between those. Okay. For this next inequality, what's different? It's an or. So let's solve this. We'll solve the first one in blue. I want to subtract 5 from both sides. So we have x is less than -8. I'll solve the other one. We'll put the word or here. It's important to carry down that compound word there. We want to subtract 5 from this also. So we have x is greater than or equal to, so 4 minus 5 is -1. So let's graph this. We'll put 0, -1, -8. So in blue, x is less than -8. So we can't include -8, and we want the numbers that are less than that. In red, we want numbers that are greater than or equal to -1. But this is an or, so it doesn't have to be true for both. Any of the numbers shaded in blue are true for the blue inequality, x is less than -8. Any of the numbers shaded on the red part of the number line are true for the second inequality. And either one of those regions, both of those regions are solutions. So we're going to say our solution is, solution set, starting from the number line left to right, -infinity to -8, not including -8, together, union with -1 to +infinity. And let's make some room to check here. Whoop. Delete that little extra. Now we got some room that we can check. So let's go to and think about checking this. Whenever you check something, you should check something that you believe to be in the solution region. So we have 2 regions to check, and you should check something that you want to make sure doesn't work. So let's start by checking something that we didn't include in this interval and make sure that it doesn't work. So we want to check something between -1 and -8. Let's just check -5. Is -5 a solution? Well, we plug it into both inequalities. -5 plus 5, is that less than 3? Well, that would be 0 less than 3. Nope. Is -5 plus 5 greater than or equal to 4? 0 greater than or equal to 4? No. We want or. Well, for an or statement, just one of them has to be true. Neither of these is true, so this implies -5 is not a solution. And we didn't expect it to be a solution. It's not in the shaded region, but we need to make sure that, you know, we've not included what we weren't supposed to include and just kind of sample. We can't possibly check all the numbers that are between -1 and -8. There's an infinite amount. Can't check all. So we just check some. So another number that we should check is something in the shaded regions. So I'm just going to give you an example. Both of them should be checked. Let's just check if 0 is included. You should check 0. 0 is one of the easiest things to check. So let's check 0. Is 0 a solution? Is 0 a solution? Well, run out of room. Let's scroll up a little bit. So we want to check both inequalities. 0 plus 5, is that less than negative 3? Is 5 less than negative 3? Nope. Let's check the other one. 0 plus 5, is that greater than or equal to 4? 5 greater than or equal to 4? Yes. And because this is an or, one of them being true is sufficient. So that we've checked a number in the red region that we are at least shading the correct direction and 0 is included. We can't possibly check all of the solutions, but we've given a sample, and it would be advised to check something in the blue region, maybe check negative 10. Okay, we're going to look at a couple more compound inequalities, not just to do more problems, but because the solutions to these are a little different. The solution regions are a little different than what we've encountered before. So here we have two inequalities joined with or. Let's go ahead and solve these. So we're going to add 6 to both sides. So we have 2a is greater than, let's see, negative 14 plus 6 is negative 8. Divide both sides by 2, and we get a is greater than negative 4. Or we're going to subtract 5 on both sides. In the second inequality, we get 3a is less than or equal to 18. Or when we divide both sides by 3, we get a is less than or equal to 6. So let's graph this. Put 0 in the middle. Negative 4, positive 6. Okay, so we're going to do a is greater than negative 4 in blue. A is greater than negative 4. We're going to graph with a to the right, shade to the right. And I'll do a is less than or equal to 6 in red. So that includes 6, and we go to the left. Now, it's tempting to say, well, I want the overlapped region because there's some overlap. So that's I must want that. But we need to slow down and we need to say, okay, what is in the solution to this? All right. So this is immediately thinking about checking. What checks? What works? And we've got an or. So it just means that one or the other has to be true. So let's check something. Let's check 0. It's shaded by both. Is 0 a solution? So we say 2 times 0 minus 6 greater than negative 14. That'd be 0 minus 6, which is negative 6. Is that greater than negative 14? Yes. We don't need to check the other one because it's an or. So we already have one that's true. So I'm going to kind of cut to the chase. 0's got to be one of the solutions, or in the solution set. So now let's check something that's red but not blue. Negative 5. Is negative 5 a solution? So we say 2 times negative 5 minus 6. Is this greater than negative 14? So that's negative 10 minus 6 is negative 16. Is that greater than negative 14? No. But it was shaded red. I should have been checking the second one anyway because that is where that red region comes from. So if I'm going to check negative 5 times 3 plus 5, is that less than or equal to 23? So we have negative 15 plus 5. Is this less than 23? Well, that's negative 10. And yes, that's less than 23. So negative 5 is the solution. What about over here? What if I were to check 7? It's in the shaded blue region. Is that going to be a solution? Yeah, it would be a solution to the first inequality because that's where we get this blue shaded. And since we have the word or, it doesn't have to be part of the red inequality shaded area. So what does this mean? We saw this in the prior video. If we have an or and we have the entire graph shaded, because we don't need to worry about overlap, then my solution is negative infinity to positive infinity, all real numbers. For our last example, let's solve this. We add 7 to both sides. 2t would be less than or equal to 12. Divide by positive 2, we get t is less than or equal to 6. Or, in this problem, we want to subtract 5 from both sides. We have negative 2t is greater than 3 minus 5 is negative 2. Divide both sides by negative 2. That will flip that inequality. Greater than becomes less than. Negative 2 divided by negative 2 is positive 1. So let's look at this on the number line. We have 0, 1, 6. So we'll do this first one in blue. T is less than or equal to 6. That shades that way. And then in red, we've got t is less than 1. And that way. Interesting. So we have some overlap. And we also have some region that's not shaded by either. And again, this is an or statement. So we just need it to be shaded by one or the other. We don't need it to be shaded by both. It could be true for one or the other. So what regions are shaded by one of the regions or the other? Let's make this a little bit bigger here. Well, certainly this is shaded by blue, and this region is shaded by both, which is okay. It just has to be true for one or the other. It can be true for both. But out in this region, we aren't shaded by either. So if we want to think, should we check 7? Let's go back to the pin here. Check 7. Is 7 a solution? And we're expecting it to be no, so let's verify that 7 should not be shaded. So 2 times 7 minus 7 is that less than or equal to 5. So we have 14 minus 7 is 7. Is 7 less than or equal to 5? No. But we have to make sure it's not a solution to the other either. So we want to check 5 minus 2 times 7. Is that greater than 3? So 5 minus 14 would be negative 9. Is that greater than 3? Nope. So 7 is not, so that implies 7 is not a solution. And that means it shouldn't be shaded, and it's not. 7 is not shaded. So we could check, we should check, and I won't for time, but check if 0 is the solution, it's shaded. Check if 5 is the solution, it's shaded by the blue but not the red. Would that work for this or statement? And it does. So our interval notation is starting from left to right, negative infinity to positive 6, including positive 6. Okay, so the ones I want you to try before coming to class, 3 of them. I want you to solve, write your answer in interval notation, and check. Now, I didn't say you have to graph, but graphing is how we write. We know what the solution set is, or at least how I do. I'm a visual person, I need to see it. So that's what I would suggest. Solve, graph, check, and write your answer in interval notation. Solve, graph, check. And then write solution in interval notation. Interval notation. Okay, so number 1, negative 10x minus 10 less than or equal to negative 20, and negative 2x minus 18 less than negative 10. Number 2, 13x plus 13 less than or equal to negative 13, or negative 5x plus 11 less than or equal to negative 4. And the third one, I kind of did the algebra for you, kind of make this a little bit quicker. X is less than negative 5, or x is less than or equal to 7. So try those, bring those back to class, and we'll check, see how you did.